Okay, so um, these, as we've said, these amplitude coefficients, as we've written kind of here, these amplitude coefficients are the projection of the arbitrary function f of x onto the basis states. I want to remind you that uh, these functions f of x are not completely arbitrary. They have to satisfy the boundary conditions, but other than that, they can essentially be arbitrary as long as they're well defined. Um, so so these coefficients are the projection of this arbitrary function onto the basis states. Okay, and so in some sense, they tell you how much of each one of these basis states to mix into this linear superposition in order to get in order to get back this arbitrary function. Okay, but it's important to keep in mind that the coefficient c sub n can actually be complex. Okay, so in general they're complex, and so besides, they also can impart a phase to this superposition of each one of the basis states, and so that's important to keep in mind. Okay, and since each eigenfunction psi sub n has an energy associated with it, E sub n, okay, then since these coefficients are related somehow to the amount of each one of these basis states which is mixed into this linear superposition, then these coefficients C sub n are also related to the probability that a measurement of the made on the wave function f of x, an energy measurement, will yield an energy equal to that eigenenergy. Okay, so again, these coefficients are projections of the arbitrary function onto the basis states, and so they're related to the probability that when you measure the energy associated with this state, that you get a particular value equal to the eigenenergy. Okay, so the important thing to understand in this is that if we're wanting to measure the energy of a wave that's associated with a state, that's associated with a wave function, then any single measurement has to on a system must yield a well-defined energy to the precision of our instrument. Okay, all right, so it must yield a number. Essentially, you make a measurement on an energy measurement. Somehow you devise an experiment to make an energy measurement of your particle that's represented by the wave function, and it has to yield a number. It can't yield a range of numbers. It can only yield a range of numbers to the extent that you have limited precision. Okay, so it has to yield a number. Okay, so, and in particular, it has to yield a number that corresponds to an eigenenergy. Okay, because the particle has to be in either an eigenstate or a linear superposition of those eigenstates. Okay, and since it has to yield a number, okay, a particular number, any given measurement has to yield a number, then that number has to correspond to an eigenenergy. Okay, so what this means practically is that if a system happens to be in an eigenstate, so if you manage to put the wave function which corresponds to the particle in an eigenstate, then it has a well-defined energy. And so if you make repeated measurements on this particle, if you repeatedly put the particle into this eigenstate and then you measure the energy, you're going to get the eigenenergy out. But if you if you have a system which is in linear superposition state, its energy is not well defined.